Hey all, this is Mr. Yeager for Physical Science. Today we're looking at waves, introducing the wave unit for physical science. So we're going to be going over characteristics of the waves. We're going to be looking at also what we measure about the waves, frequency, wavelength, velocity, or speed, and trying to describe the different types of features of waves themselves. You're going to see lots of pictures in this because fortunately there's plenty of visuals with the waves, and we'll go from there. Okay. So, the thing about waves, okay? Waves basically are this repeating disturbance in space. Whenever I'm doing this lecture in class, I'm always moving my hand up and down like a wave, all right? So a wave is a disturbance in space. One of the key things is that it transfers energy, okay? Waves are able to transfer some amount of energy through matter, which we call oftentimes during this unit a medium. Okay, what are the waves traveling through? We call that the medium. All right. So waves transfer energy. That's very, very important. Okay. So they transfer that energy through space or matter. Okay. So here's basically repeating it again. Wave is a vibration or disturbance in space, and a medium is the substance that it travels through. Okay. So what I have in class is just basically a bunch of different videos that I share with them to kind of show these different types of waves like sound, earthquakes, and lasers, again, of the energy passing through. Now, one thing that doesn't move through is, I want to write this right now before we read the mechanical, is waves transfer energy, not matter. They do not transfer matter. So when you see an ocean wave, that water did not come from the center of the ocean. The energy might have come from the center of the ocean, but all it's doing is displacing the water as it travels on down, creating that wave. All right. So waves move energy, not matter. Now there's a couple types of waves out there that we're going to be looking at. There's what's called mechanical waves. Mechanical waves are waves that you need, that they only travel through a medium. You need a medium, all right? It has to travel through an object. Examples of this, ocean waves. That's a clear, easy visual one. But the other one that we're going to definitely study later on is sound. You cannot make sound travel unless there's something for it to travel through, unless you move matter. So you cannot hear my voice without me basically vibrating the air in front of me. All right, so we'll come back to that when we do a whole talk on sound. The other type out there is electromagnetic. Okay, it does not need, I love that poor spelling there. Okay, it does not need a matter or medium to transfer the energy. It doesn't need matter or matter or a medium to transfer through. So mechanical, medium. Mechanical needs a medium. All right. Electromagnetic, or EM as we'll call it. Again, we'll come back to that in another talk. It doesn't need a medium. The only example of electromagnetic waves is basically light. We're going to learn that radio, X-rays, all that stuff is just a different form of light. Okay. So electromagnetic waves do not need a medium. Mechanical waves need a medium. So that might be something we have to figure out, is it'll say, which of the following is a mechanical wave? Example of a mechanical wave. Find the example where you need something to travel through, a medium to travel through. All right, now I know I just said there are two main types of waves. All right, those are two basically we can say categories of waves. It's mechanical and electromagnetic. This is basically the two main types of travel for waves. The two types of ways that waves travel. Okay, I use that word instead. They can either travel through what's called transverse or compressional longitudinal motion. Okay, transverse is one. Compression longitudinal, they're interchangeable. You have to be ready to manage both terms for it. All right. So what does that mean? A compression wave or a longitudinal wave is one where the wave travels in the same direction as it moves. The wave itself oscillates. Okay, that one word we're going to be using a lot is oscillating. Oops, let me try spelling that again. O-S-C-I-L-L-A-T-E. Okay, oscillate means to move back and forth. So a compression wave is one where it's if you look at this picture down here, is where the wave gets squeezed. So the wave is getting squeezed and then it gets stretched. So it's a motion where basically the wave is moving back and forth like this, or it looks like it's moving back and forth like that. But all of the energy is traveling down the slinky as it moves. That wave carries energy. So the example of a compression wave would be something like a slinky, where you kind of pulsate it. It's going to be a pulse, okay? That would be a compression wave, all right? And here's basically a little animation of that, where this is a compression wave. Not one where it goes up and down. That's probably the one you're thinking about, is the one where the spring swings up and down. This is vibrating through it, okay? Here's just another example of it. This would be a compression wave, where basically you can see right here, it's going to stop moving when I do this, okay? You have something that's pushing it, that's pulsating it, and it causes the dots to start moving. Now, one thing I always try to point out to the students on this is, if you look at this carefully and try to focus on one dot, you'll see that one dot just keeps going back and forth, back and forth. I mean, you could pick any dot throughout this, focus on one dot, and all it does is move back and forth. It looks like that the dots travel all the way down the tube, but a wave does not carry matter. The dots are little pieces of matter, so we're not carrying the matter, but it is carrying this energy that's passing through all of the dots. Okay. So to create a wave, you need to create a disturbance or pulse at one end of the slinky. That energy is then transferred to the next coil and the next, and so on. All right. What are the parts of a compression wave? Okay. A compression wave basically has two parts. One part is the compression. One part is what's called the rarefaction, which I'm sure that's a new word. A compression is the area of the wave where it's squeezed. So in this picture over here, it's basically in the really red area. That's supposed to be a bunch of lines all squeezed together. And so that's a compression. The area in front and behind it is a rarefaction. Okay. So that's what I mean by oscillating, is it's going to oscillate back and forth between rarefaction, compression, rarefaction, compression. It keeps on going back and forth. So compression is the squeezing area, rarefaction is the stretching area. This is just another picture trying to show that some. Okay. It turns out sound is a longitudinal wave. All right, so that's going to be an important thing. Sound travels as a longitudinal wave. So you can see the animation with the tuning fork there. The idea of a tuning fork is when you hit it, it vibrates, and what it does is it pulls the air in and then pushes it out. It pulls it in and pushes it out very, very, very quickly, so it compresses some of the air particles and then stretches them out back and forth, back and forth. That we then are able to hear as sound when it travels to our ear and hits our eardrums. So here's just another, again, picture of it. All right, compression is we got a compression at A, rarefaction at B, compression at C, rarefaction at D, alternating, alternating, alternating. The transverse wave is the one that you probably know a little bit better about. That's the one where the object's being whipped up and down, up and down. We say that the wave is traveling perpendicular to the motion. So the energy is traveling to the right, but the wave is going to travel up and down, up and down, up and down. The matter is traveling up and down. Okay? So again, that's what we mean by oscillation. One oscillation would be one complete up and down motion. That would be one oscillation. The parts of a transverse wave, the high points are called the crest. That's probably known if you've ever been to the ocean. It's the crest of the wave. The bottom part of the wave that you usually don't really see is the trough, pronounced trough. So crests are the top, troughs are the bottom on a transverse wave. So we need to be able to understand the different parts of a transverse wave. So we need to know what a crest, trough, wavelength, and amplitude is. So we just went over crest and trough. Crest is the top, trough is the bottom. The word amplitude means height. Basically, how tall is the wave? All right? The height of the wave. This is always, always, always measured from the middle of the wave. Okay? So the amplitude would be this part up. Now you can't even see it anymore. The amplitude would be this part up. Or we can measure it going down. But we should basically see that they are the same as long as the wave is consistent. Okay? But we always measure from the middle line up or the middle line down, never from the very top to the very bottom. All right, so that's amplitude, the height. Wavelength is the distance of one wave. So there's lots of ways you can figure this out. The easiest way for most students is measure crest to crest. Okay, the distance from crest to crest is the wavelength. All right, but is the length of one wave, one up and down motion. So this goes down and then up and comes back to the middle. That is one entire wave. We can also say it's trough to trough. So again, to review, you got your longitudinal wave. It moves in the direction that the energy is moving, made up of compressions and rarefactions. Transverse waves, they move perpendicular to the motion. The wave's moving to the right, but the object's moving up and down. Top is crest, bottom is trough. Amplitude's the height. Wavelength is one wave, one crest to another crest. Okay. So let's just identify these. This type right here would be a longitudinal wave. This one right here would be a transverse wave. And then down here, the first one would be longitudinal, and the second one would be transverse. Okay? So that is going over I mean, it's a lot of terminology. Mechanical waves, electromagnetic waves, transverse, longitudinal, crest, trough, compression, rarefaction, amplitude. A lot of terminology to already kind of start off with in this unit. Okay? So a wave can transmit what? Energy without transferring matter. And then the shortest distance between 2 points on a wave where the wave pattern is repeated is called the wavelength. Okay? So this is just breaking down the two parts of transverse and compression waves. All right. Again, oscillating at right angles, perpendicular, oscillating in line. We're going to see that transverse waves can travel through a vacuum. When we talk about electromagnetic, which is the ones that can travel through a vacuum, they're always transverse. There's no compression wave that can travel through a vacuum. There is none. Okay? Because again, it turns out with the compression wave, you need some sort of particles to move through it. The parts of a wave, transverse, crest, trough, compression, rarefaction. So to finish up, we're going to look at a couple more characteristics of the waves in terms of, let's talk about the objects, the wave's frequency. We already mentioned amplitude, but we'll talk about that again. And then wavelength and speed. So, let me move this out of the way. Frequency, which the symbol for it is lowercase f. I'm going to change colors, it's a little tough to see on that. Lowercase f. All right. Frequency is saying how many waves pass every single second. How many waves, oscillations, pulses, all those words are the same. How many objects pass you every single second? This is measured in hertz. So frequency equals waves divided by time. Okay. Frequency is waves divided by time. That's how you can solve for it. Waves divided by time. All right. That is the frequency. All right. How many waves pass every single second? Amplitude, we already mentioned it, is the maximum displacement, the height or the depth of the wave. You can calculate it from, if you measure the distance from highest to lowest, you can half it. I don't recommend that too much though. We have what's called the wavelength. The wavelength is the length of one wave. It does have an interesting symbol. It's this thing right here called the lambda that I draw that way. All right. That is the distance. Wavelength is measured in meters. Okay, I think I have that right down there. All right, it always bothers me when I go, what's wavelength measured in? And people are like, I don't know. Well, what's length measured in? Meters. Okay, it's always measured in meters. So this is the length of one entire wave. Symbol for it is this lambda figure. Okay. We also have what's called the speed. All right, we've talked about that a little bit here and there. We haven't done motion per se yet. So speed is always equal to. Oops, sorry. We can find speed by doing distance over time, but we're going to actually have another formula for it too. But I mean, you know, the term speed just means how fast it's moving. Then there's also something else that we might measure called the period. The period has the symbol capital T. Capital T, and this is the time for one oscillation. the time for one oscillation. So period equals time over waves, which is the opposite of frequency. All right? Period is a measurement of time, so it's measured in seconds. But if you know the period, you know the frequency. If you know the frequency, you know the period. They are inverses of each other. All right? Frequency, one more time, is waves over time. So all that's different here is which one's on top. Frequency is counting, period is measuring time. So if you actually want to calculate the speed of the wave, and you don't have the distance and the time, we can use this formula right here. Velocity equals frequency times wavelength. Okay? If you have the frequency and the wavelength, you just multiply those two things together. So if we do a couple quick problems, if a wave has a velocity of 250 meters per second and a wavelength of 6 meters, what is the frequency of the wave? So this is the velocity, here's the wavelength. Formula V equals wavelength times frequency. I can do a triangle if you prefer that method. Velocity is on top, frequency and wavelength on the bottom. If I'm solving for frequency, I'm going to do velocity over wavelength. So velocity over wavelength, 250 divided by 6. All right, I think the answer comes up here, so we just divide the two. Yep, there we go. 42 hertz. What is this saying? What does this mean? There's 42 waves every single second. That's what that is saying. There's 42 waves passing you every single second. So let's make sure we know what frequency really means. Here's another example. The piano string tuned to middle C vibrates with a frequency of 264 hertz. So I'm given the frequency this time. Assuming the speed of sound in air is 343 meters per second, find the wavelength produced by the sound. So for this one, I got velocity equals frequency over wavelength. Wavelength equals velocity over frequency. And then I divide those. Sorry, there should be a division here. It's kind of a little confusing there. Let's do that. This should be 343, divided by 264. And then my answer is 1.3 meters. Okay, 1.3 meters. All right, that's how long one wave is. So again, here's our formulas. Here's the rearrangement of the different formulas that you might have to solve for in this unit. All right. Here's one more example. I'll let you kind of read through that. All right. Actually, I will do one part of it real fast. It does talk about this. This is something that I usually have students struggle with a little bit. This problem is saying that there's 40 vibrations in 30 seconds. Also, a given maximum travels 425 centimeters in 10 seconds. So this one's worth doing. So they don't give you frequency, they don't give you velocity, they don't give you wavelength. This is not the wavelength. They almost always are very clear that they will say the length of a wave, or the wavelength is this. Okay? The wavelength is blank. Just a second, sorry. All right, quick interruption there, sorry. So, going back to it, you're given vibrations, you're given time, you're given distance that the object travels, and then you're given the time that it takes to travel that far. So this would probably be the most difficult that they can make the problem. So what you see here is you solve for the frequency first. Frequency is vibrations over time, so you got your frequency. Then you use your distance and divide that by this time, the time that it takes to travel. That gives you your velocity. And then finally, we can then go to our actual wave equation and solve for the wavelength in this particular problem. So that's as difficult as these problems can become. You just have to make sure you read correctly. Like I was saying right before the interruption there a little bit, is that be careful with distance, all right? It'll say very clearly whether it's a wavelength or length of the wave, or this is how far the object travels, okay? A couple last things, relationships, okay? Frequency and wavelength are inversely related to each other. You can see the picture down here. As you increase the frequency, the waves get closer and closer and closer together. So high frequency means small wavelength. Low frequency means large wavelength. So they are inversely related. Another thing that may come up, especially when we get to light, is how is energy related? We'll see that frequency and energy are directly related. Why is that? Think about going to the beach with ocean waves. If there's a high frequency of ocean waves where lots of waves are crashing in and you try to swim out, you got to use a lot more energy to overcome that large frequency of waves. So more waves means more energy being carried in. All right? So if frequency or energy are directly related, that means wavelength and energy are inversely related. So if I have a high frequency wave and a low frequency wave, this would have high frequency, low wavelength, small wavelength, but high energy. So frequency and energy go together. E and F go together. Over here I have low frequency, high wavelength, and low energy. All right, so again, E and F go together. All right, and I think that's pretty much it. So I mean, quite a bit of terms to go through. I'll obviously go back to look over anything that maybe went a little too quickly on, if you think so. But just quite a bit of terminology to start learning about waves, and we're going to use it from there. Thank you.